Our next speaker is Saikia, and she'll be talking about Lorentz factors of compact jets in black hole X-ray binaries.
Okay.
Stick ahead.
Can you hear me and can you see the slides?
Yeah.
Perfect. Good morning or good afternoon, everyone, depending on where you are connecting from right now. And thanks to the organizers of the conference for some very fruitful sessions in the last few days and for giving me this opportunity to present my work here. I'm Saikia from New York University, Abu Dhabi. In this presentation, I will talk about stellar mass black holes and how fast or how relativistic their jets are. Relativistic jets are a fundamental aspect of accretion onto black holes on all scales from X-ray binaries to AGN. They are highly energetic, strong, narrow, relativistic collimated outflows, which comes out of the X-ray binary system at some points of its evolution. These jets carry away a large fraction of the available accretion power and is one of the main ways through which accreting black holes provide kinetic feedback to the surrounding medium. Now, at the first approximation, the light or the emission from a jet can be simply modeled using two main parameters: the inclination angle of the jet with respect to our line of sight, and the Lorentz factor, which tells us how fast or how relativistic these jets are. Now, although with better observations and better techniques, we can estimate the inclination angle of few of these sources, but it is extremely hard to measure the Lorentz factor for them. Till date, we have very few highly uncertain estimates of Lorentz factors in just some black hole X-ray binaries. So the goal of the study that I'm presenting today was to constrain the Lorentz factor of the compact jets in several of these black holes using a new method, and to estimate the parent distribution of Lorentz factors expected for X-ray binaries as a population. So for this study, we adopt a simple model along with infrared observations of these X-ray binaries through its complete outburst cycle. So normally when we observe an X-ray binary during an outburst, the infrared emission comes from both the disk and the jet. So here is a typical light curve in infrared of one such black hole X-ray binary during the outburst. Now, if the infrared emission was coming only from the disk, then this is the kind of light curve that one would expect to see. But in many X-ray binaries, we do not see this simple straightforward light curve. We find bumps, that means excess of infrared emission whenever the jet switches on. This infrared excess is thought to be coming from the jet emission. And while in some sources, this infrared excess is prominent, in some other sources, it is either negligible or entirely absent. So we use this presence and absence of infrared excess, along with the amplitude of this excess, to shed light on the Lorentz factor of these sources. We think that the two parameters, the inclination and the Lorentz factor, together can explain the amplitude of this infrared excess in different X-ray binaries. First, let's talk about inclination. If the inclination angle is small or the jet is directly pointing at us, then we can definitely expect excess of near infrared emission because of relativistic beaming. Now, as we increase the inclination, less and less synchrotron will be seen. So this amplitude of the excess will drop. But when the inclination angle becomes large enough, then we can again expect to see an excess of emission, because at high inclination, very little emission is coming from the disk, as the projected area of the edge on disk will be small. And hence the rise of the jet emission with respect to the disk will be high. So basically, this is what our very simple model says. X-axis is inclination and the Y is the amplitude of infrared excess observed. And the different colored curves are the predicted values for infrared excess for different possible Lorentz factors. So very low or very high inclination means the infrared excess can be high depending on the Lorentz factor. But in the moderate inclination range, something between 30 to 60 degrees, we do not expect high infrared excess, whatever be the Lorentz factor. Okay, so far so good, but does real observations follow these simple predictions? Well, these are all the observations that we have till now of X-ray binaries with reliable measurements of both infrared excess seen during state transition and inclination angle. And as you can see here, all the data points lie in the space proposed by the model. Now the next question is, from these observations and from the proposed model, can we constrain the Lorentz factor for these X-ray binaries in our sample? The answer again is yes. So here again is a table of all the X-ray binaries for which we have reliable estimates of measured infrared excess. We have tabulated here the observed infrared magnitude change, and we can calculate the same using our model and the known parameters of the system, like the orbital period, masses, etc. For example, by using the physical information of the source, like the orbital period, black hole mass of companion star mass, and inclination angle, we can calculate the projected area of the accretion disk, thereby predicting the expected disk emission at infrared. Similarly, we can also calculate the expected jet emission at infrared wavelength for known inclination angle and many possible Lorentz factors. So we have the calculated disk emission and the jet emission. And using these two, we can calculate the expected amplitude of the excess, which is basically the combined emission coming from the disk and the jet divided by the emission coming from the disk alone. Now we use Bayesian statistics to compare the observed excess and the different calculated excesses for different Lorentz factors, and use it to constrain the Lorentz factors for which the calculated infrared excess distribution best matches with the observed one. I'll very briefly touch on the Bayesian analysis part of the work without getting too much into the details. But briefly, in order to find the best fit parameters, in our case, the Lorentz factors, we needed to find and maximize the posterior probability density function, for which we needed mainly phi. That means the parameters of the black hole system, like mass, orbital period, inclination angle, etc. We need gamma, the Lorentz factor of the individual sources, the parent Lorentz factor distribution, the observed infrared excess data, and the model. Using these, we calculate all the terms involved in the Bayesian inference. I will not go deeper in the method due to time constraint, but if you want the details, please do have a look at the paper. Moving on now to the most interesting part, that means the results we obtained by carrying out the MCMC simulation of this Bayesian inference. We are able to constrain for the first time properly the Lorentz factor of the compact jets for all the 9 sources in our sample. Here you have all the 9 X-ray binaries. The x-axis is the probable Lorentz factors for which we tested the model. And what we are showing are the histograms normalized by peak of the inferred jet Lorentz factors constructed using the MCMC sample. We find that the Lorentz factors of most of the black hole X-ray binary jets are quite low. For example, it is around 1.6 for XTE 1550, which is shown here in the first plot at the middle line. It's around 1.9 for MAXI 1836, shown here in the second last plot, and around 2.5 for XTE 1859, shown here in the last plot of this panel. So for this method, to succeed in constraining the Lorentz factor for these individual sources, we need good estimates of the inclination angle and a precise measurement of the observed infrared excess. For 2 of the sources, yeah, sure, it's almost in the end. For 2 of the sources in our sample that did not have well-constrained values of observed infrared excess, that means either had limits or model-dependent values, we can only provide limits on the Lorentz factor. For example, 1655 and SWIFT 1753, we can well constrain only the lower limits of Lorentz factors. But for all the sources with reliable measurements of inclination angle and good measurement of the observed infrared excess, where we could constrain the Lorentz factors, we find that they lied in the range of 1.5 to around 3.5 or 4. It is also interesting to note that assuming the parent Lorentz factor distribution of stellar mass black holes also follow a power law curve, just like the AGN jets do, we find that the power law index of the distribution is around minus 1.8 or 1.9, which is quite similar to what is expected for AGN2. For example, the power law index of AGN Lorentz factor distributions reported in previous studies are seen to be around minus 1.5 to say minus 2.3, which was a very interesting observation that we had, but we have not looked at it further. So finally, to conclude, we studied a sample of black hole X-ray binaries with near infrared observations with the goal to estimate how fast their jets are. The tool we used is the infrared excess that is detected when the jet switches on in these systems. We used a very simple model of inclination angles and beaming parameters to explain why different X-ray binaries have different amplitudes of infrared excess. And for the first time, using Bayesian analysis, we could constrain the Lorentz factors for several black hole X-ray binaries using this method to be roughly between 1.5 to 3.5. Also, as an end note, these results demonstrate that infrared monitoring can be really useful for X-ray binaries over state transitions to study these jet properties. And we hope to have more infrared detections of these transients during transitions so as to test this model and make it more reliable. Thank you for your attention.
Thank you, Payaswini. Any questions in the room? We have one.
Hello, this is Andrzej Ściałski. I noticed on one of your videos you defined the Doppler boosting factor for the jet as average of the squares of Doppler factors for the approaching and receding jets. And I'm puzzled. It seems to be not the correct way to do it. Can you comment on that?
Yeah,
this one.
Yeah, this one, yes. So we used this equation from a previous paper, which it was just to get an idea of how much could be the relativistic beaming from the approaching and the receding jet.
Well, I think it's incorrect, but
okay.
Maybe you can derive
like
it
know
yourself.
how, if you had a better idea of how to go about this, I would love to know about this.
I see lots of hands up on Zoom. Jury, do you want to go?
Yes, hello. I'm wondering about this infrared excess, because we have in the couple of papers, we have shown that in XT1550, the infrared excess starts with the very hot spectrum, alpha 1 plus 6, and this is clearly inconsistent with the emission from the jet. Or it's actually not 1.6, but anyway, with a very positive slope. And also for GX39-4, we showed in the paper by Kosenkov last year that the infrared excess is actually very stable, has a very stable slope with alpha 0. And there's a jet that is seen in the WISE data has a very variable component, which is actually cut off much before the near infrared. So my feeling is that at least some of the emission that you claim is to be produced by the jet is not produced by the jet, but is produced by something else. And our interpretation is a hot flow, but it's clearly there are a couple of components there in addition to the irradiated disk. So I'm wondering whether this will affect, of course, your results, I hope, because I mean, basically some of the emission is coming from different component, which is related to the accretion, not to the jet. Maybe you can comment on that.
Yes, that's actually a very valid question, because this depends on the assumption that the near infrared excess is coming from the jet. We did try to check for this correlation when the gamma is 1, that means there is no jet emission, and we did not see any correlation between the observed infrared excess and the estimated one, which we are using our equations. So we think that it should be the jet which is giving the near infrared emission, the excess that is coming. But this whole model is based on the fact that the near infrared is coming from the jet. So that is a caveat that we discuss in the papers.
Another question from the room?
Yes. Actually, I may have missed the point, but did you make some comparison between your estimate of the jet velocity with those that have been done from radio observations, for example? I don't know if they exist.
Yes, we did actually. And wait, let me check if I have it here. Yes, so we have checked with a few of the, I mean, these are few of the, I just put one of the paper, paragraph from the paper. We have looked at some of the Lorentz factors that we see in other sources, and they are around the same kind of level that we see here. But for all the 9 sources for which we had the measurement of infrared excess and inclination, there have not been any for which there is direct comparison. There is the direct estimation of the Lorentz factor to compare directly yet. But that is because we have only 9 sources right now in our sample.
All right, we'll take one from Zoom. Mukesh.
Hi. If I'm seeing it correctly, are you assuming that the total jet power is constant among all the sources? Because the excess should be depending upon the respective jet powers apart from the inclination angle.
Yeah, that is true. But we are not assuming that the extra luminosity or the jet power or the direct power is similar in all of these. For example, we actually tried to have a look if infrared excess does follow a trend with the extra luminosity or the total jet power or the total bolometric power or something like that to get an estimation. So there have been only two sources for now. One is 1550, which we see that it has the same infrared excess, whatever be the extra luminosity. I know that extra luminosity is not the proper estimate of the jet power, but it still gives an idea of how the bolometric power of what is the bolometric power of the source, and if it should depend on the if the infrared excess should depend on this.
Okay, thanks.
One final question. Any takers? If not, let's thank Payaswini again.